You have options when it comes to PASCO temperature sensors. Let us introduce you to the wireless thermocouple sensor. With the smallest thermal mass of all our wireless temperature sensors, it is the best choice when you need accurate temperature measurements that occur very quickly or under extreme temperature conditions. The wireless thermocouple sensor includes a Type K probe, which plugs into the sensor box. Match up the prongs with the plug by width. Or if the plug won't go in, try flipping it over. This sensor is rechargeable and it comes with a charging cable. When you turn on the sensor, its default temperature unit is degrees Celsius, but you can change to degrees Fahrenheit or kelvins by double-clicking the power button. When you see the unit you want, stop double-clicking. The ambient temperature in the room is about 29 degrees Celsius. Notice the holes on the top and bottom of the sensor box. These holes help ensure the sensor box is at ambient temperature. For best accuracy, make sure the sensor box is placed somewhere that matches the ambient temperature conditions. You can long press the power button to turn the sensor off, or leave it on and it will turn off by itself after 1 hour. As we've seen, you can use this sensor independently, or you can connect it to PASCO software like SparkView, Capstone, or ChemView. I've already connected to SparkView via Bluetooth, and I'll choose a digits and graph display. Once you connect to software, the sensor can record and display data like other wireless sensors, so you can experience the data visualization and analysis of your choice. Previously, I mentioned the sensor is a great choice when working with temperature extremes or when temperature changes rapidly, so of course that makes me think of fire. So my lab partner and I are going to explore the temperature of a candle flame as we move through it. We checked ahead of time to make sure the temperature of a burning candle couldn't produce a flame temperature outside the probe specs. We found that a Bunsen burner at its highest efficiency is beyond the specs of this probe. We will keep the insulating wrap from getting in that flame because it has a lower heat tolerance than the sensing part of the probe, which is these last couple of millimeters at the end of the probe where the two wires are welded together. Now I'll start recording data. Beginning at the dark zone near the wick, there's no glowing flame here. This is where unburnt wax is rising. The wax evaporates by heat from the surrounding reaction, but it is not burning because it doesn't have enough oxygen mixed in with the fuel to combust. And now, up into the luminous orange zone. Combustion is happening here because oxygen has mixed with fuel, but the gases aren't in the ideal mixture. So, some of the reactions aren't combusting all at once, and here we can see the temperature is higher. How could you use the probe to explore whether there is an even hotter location where full combustion might be occurring? Try it for yourself, ideally in a room less drafty than our studio. Now let's see how the opposite extreme works with some dry ice. Let me stop and start a new run. My new run is the green run. There's the dry ice. At the surface where it's sublimating, temperature is pretty cold. It's getting lower and lower. And we can see right now at this surface, it's cooling down. Temperature it's about negative 70 degrees Celsius. You can see how the probe itself is responsive in very hot or very cold solids, liquids, and gases. You could also just tape or attach the probe tip to the outside of a glass, metal, or ceramic vessel to get its surface temperature. This probe can be used for many investigations, such as monitoring the heating rate of a stove element at oven temperatures, or determining how much thermal energy is moved by a heat exchanger. Visit the product page linked in the description to learn more about the wireless thermocouple sensor, including specifications and links to lab investigations. Thanks for watching.